So solution, what do you guys have down for that?
Is that one or more substances?
Homogeneous mixture? So are liquids the only thing that can be, no, what's the other thing that can be a solution?
Could be solids or gases?
Yep, solids or gases could be. The solid that can be would be something like an alloy. So you guys made brass last term, and that brass that you made was a homogeneous mixture of zinc and copper. And so a true solution. So solute solvents, more. Oops. Less. More. That's it. Whichever one you have more of, that's your solvent, and whichever one you have less of, that's your solute. Nothing else to it. So what happens when the solubility of a solid? Okay, so our temperature is going down, and what happens to the solubility of solids? It also goes down. And why does it go down? The solvent has less kinetic energy. And so since they have less kinetic energy, they have less of an ability to break apart the solid. What about gases if I increase the temperature? So temp goes up, and what happens to gas solubility? Same situation going down, just for the opposite effect. And why are they going down? What happens to them? Yep, they gain enough kinetic energy to because they're gases, so they'll just simply leave the solution. Molarity, so capital M is equal to moles solute liters of solution. So then your units will be moles per liter. What's the concentration reported in Runners 140 grams? Okay, so I want moles per liter, and what I have right here are grams and milliliters. So you can turn grams into moles, and you can turn milliliters into liters. So we'll start off with 140 grams in 100 milliliters. And for every 1,000 milliliters, I have 1 liter, so the milliliters cancel. And then moles of Ki, and then Ki grams. So then we'll just look on the periodic table and figure out what the grams per mole is for potassium iodide. So we've got 39.0983 plus 126. .9045. Yeah, looks like 166.003. And so then my moles per liter, so I got 140 divided by my 166 times 10. Looks like 8.4 moles per liter for that concentration. So then we want to look at page 4 from the notes. So at, what was it, 20 and 10, all right? So at 20 and 10, so we've got the 10 down here and the 20 down here. And if I take the 10 all the way up, I can see it can fit about 135 grams. And then at 20, I can fit about, I don't know, 145 grams. So to answer this question, we'd say yes at 140. So at 20 degrees Celsius, yes, all of the 140 grams is going to fit. But at 10 degrees Celsius, the answer would be no. There'd be 5 grams just sitting at the bottom, not dissolved. Explain how you make a 250 milliliter, 3.5 molar sodium hydroxide solution. Okay, so we have moles per liter. We need to know how many grams of sodium hydroxide to put in there, and we need a 250 milliliter vol flask. So I'll start off with 3.5 moles per liter, and I've got 0.25 liters. That's 250 milliliters, so that cancels out. And it's sodium hydroxide. So 1.0795 plus 15.9994 plus 22.98977. So I got 39.9971 grams of NaOH for every 1 mole. Oops, I put that in upside down. For every 1 mole of NaOH. So 39.9971 grams NaOH. And so times 0.35 times 0.25. And so I get 3.5 grams of NaOH. So to answer this, I would probably say get 3.5 grams NaOH. Get a 250 milliliter vol flask. Three, you're going to want to half fill with water and mix, and then fill near line. And fifth, fill to the line with dropper. Okay, contrast molarity and molality. So molarity is moles over a volume. So this is volume based, and then this one is mass based. The good thing about the molarity one is it's easy and it's inexpensive. The good thing about the mass one is it's more accurate. But the bad thing about it is expensive. And the bad thing about the molarity one is it's temperature dependent. So if you've got a vast temperature change, you'll have changes in concentration. And so this guy is temp independent. We don't care what happens to the temperature if we're calculating everything based off of mass.